Oh, shoot. And I'm just going to put this warm up. I think everybody's been in class, so I'm recording it anyways, but yeah. So 4 times x minus 3 over 2 to the n. We are looking to see where does this series converge and what is the sum of that series. Be very careful, your n is starting at 0 on this series. Your n is starting at 0. Well, probably the same R. You guys are getting x in your R value, right? Is that what you got? X minus 3 over 2 for your R value? Yeah. And 4 for your A value? Yeah. And so our sum is going to be A over 1 minus R. So our sum is going to be 4 over 1 minus x minus 3 over 2, which is just 4 over 2 minus x minus 3 over 2. And so if I'm going to keep putting it together, that's going to give me 4 over 2 minus x plus 3 over 2, which is 4 times 2 over 5 minus x, or my sum. I'm getting a sum of 8 over 5 minus x. But that is only true when the absolute value of R is less than 1. So now we have to figure out when that's true. And remember, when you have a 3-part inequality, you set it up as or when you have an absolute value less than 1, it turns into a 3-part inequality. It means that quantity is bounded between -1 and +1. What'd you get as your interval of convergence? What'd you get, Andrew, as your interval of convergence?
X is less than, or x is less than 5 and x is greater than 1.
Less than 5, greater than 1. I think I'm getting the same thing. X is bounded between 1 and 5. Less than 5, bigger than 1. And so we would say on the interval 1 to 5. So that sum exists, and that series converges on the interval from 1 to 5. You guys have any questions on geometric series, whether they have x's or not, how to find the sum and how to find the interval of convergence? That's okay?
When do you use brackets again?
Good question. So you will use brackets in a minute when we talk about something called a ratio test. So I'm going to show you. We're going to get there right now. Absolutely. Yes. So any questions, guys, on those warm-ups?
Yeah.
So looking at our series, what we notice about this series is this series is a little different than the series above it, because the series above it, in the series above it, all of our terms, every single one of our terms was numeric. But in the bottom one, this guy actually has numbers, but it also has x's raised to powers. X to the first, x to the second, x to the third. So we describe these types of series where you have x raised to a power with other stuff, other coefficients going on, but x raised to a power. This is called a power series. It's an infinite polynomial, and they are so powerful. I mean, really, if you're an engineer or you're in any kind of sciences, you're going to see these things happen. They are what we call infinite series, but infinite power series. In fact, the first calculators, like if you ever wondered, how do they determine e raised to a number? Like, how do they get these things on calculators to do these things? Because e is an irrational number, right? And to raise it to something, how do you get it to do things? Well, often what they do is they program things on the back end, and like graphing calculators, what they do is they rewrite expressions as infinite polynomials. And so these guys are so important. All right, so the most basic power series is this power series right here. That's the series n equals 0 to infinity of x to the n. If I write this out, on what interval does that power series converge? And more than that, what is the sum of the series? So on what interval does this basic power series converge? And what is the sum of the series on that interval? This one's even easier than the one we did before. This guy's another power series, or a geometric series, isn't it? It's geometric because n is only in the exponent. And so that means that this guy's geometric. And so if I was to list out these terms, I would have x to the 0, which is 1, and then I would have x to the first, and then I would have x to the second, and then I would have x to the third, and x to the fourth, and it'd go forever and ever and ever, right? And my a value in this is 1, and my r value is x. And for it to converge, I need the absolute value of x to be less than 1, or in other words, I need x to be in between -1 to 1. And so we would say that the series converges on this interval, -1 to 1. And see if you guys agree with me, right? And what's the sum? What is the sum?
1 over 1 minus x.
1 over 1 minus x. The sum is a over 1 minus r, which is 1 over 1 minus x. And so what that actually says is that if I was to add 1 plus x squared plus x to the third plus x to the fourth forever and ever and ever, and I was looking at the x values from -1 to 1, that those two expressions would be equal. That's what that says. That infinite polynomial, okay, that infinite polynomial on this interval, whoa, right here, equals this. That's what it says. Power series give us another way to write functions. I'm going to show you what that means. I'm going to write this down. So we've got what? 1 over 1 minus x. That's my sum. And I have the infinite polynomial, 1 plus x squared plus x cubed. And what we've just done is said that that infinite polynomial, that power series, equals this guy on the interval from -1 to 1. So let's picture that. Let's picture that. Okay. Here is my infinite series. Here is my polynomial function 1 over 1 minus x. See that? That's this guy. And I'm claiming that that's equal to an infinite polynomial on the interval from -1 to 1. So let me set something up. That means that if I was to look at 1 plus x, and then I was to look at 1 plus x raised to the second, and then I was to look at 1 plus x raised to the second plus x raised to the third, what I'm claiming is that as you keep going and making these polynomials, as we keep going, this right here, these graphs are going to get closer and closer and closer to the red curve. That's what I'm saying. Let me write this as a sum. It's for you, James, because I know you like Desmos. So first of all, I'm claiming this is only true on the interval from -1 to 1. So let me zoom in to -1 to +1. And let's write this as a summation, right? So we want to go from n equals 0, and I want to put a power up here, so I'll just call it p. And I'm going to make it x to the nth power. So here's my infinite summation, and I'm making it p because that's going to be where I start. So right now I start at, this one up here has 3, but I'm going to change my p value and go from 0 to, let's say, 25. I'm going to go by integers. And so what's going to, I don't want red. I want a different color so I can compare. So I want the blue curve, and watch what happens over time. So as p is 2, that puts me up here at this polynomial, 1 plus x squared. When p is 3, it gives me this polynomial. When p is 4, it gives me this polynomial function. When p is 5, it gives me this one. Do you see what I'm doing? So what happens over time? What's happening? Do you see what happens? And that's just 25. That's just going out to 25, right? Let me go one direction only. That's only going out to 25. Do you see how, whoa, slow him down. He's going way too fast. There we go. Make him a little slower. But over time, what's happening to that polynomial? See, as I get bigger and bigger, do you see how the blue curve and the red curve? On this interval, -1 to 1, not outside it, right? Not outside it. But on that interval from -1 to 1, that blue curve, which is this infinite polynomial, is approaching the red curve, which is that function, that sum. Do you see how visually what's happening here? Now, okay, I'm already getting goosebumps. I really did. I got goosebumps earlier, but this is how profound this is. By the end of next week, we will be able to take cosine and sine, which are trigonometric functions, and rewrite them as infinite polynomials that converge not only on an interval, but all the way. Well, at least e to the x goes all the way. So, anyways, we have some really cool stuff going. All right, Tina. No more of that picture. But does that help you see what we're doing a little bit? We've got this sum, and we're showing that it's equal to this infinite polynomial on a specific region. So this guy, like you said, James, is not geometric. It's got this n on the bottom. So in order to determine an interval of convergence for these types of power series, we need something called the ratio test. And I'm going to pull up the ratio test for us. All right? We need something called the ratio test. And this is what we use to determine interval of convergence actually, you use it a lot of times. It's a test you can use for any series, but we are specifically going to use it as a tool to determine the interval of convergence for power series. Specifically those that aren't geometric, but it always works. And the ratio test, let me show you it. Here, hang on. I have a different page here, and I'll show you what the ratio test is, and then we'll come back. So that's the ratio test right here. The ratio test says that to determine if a power series converges, we can look at the limit of two terms, the n plus first term and the nth term. And if we divide those two terms, or in other words, look at the ratio of those two terms in absolute value, and we get a number L, then that number, if it's less than 1, is where the series converges. If that number is greater than 1, then that's where the series diverges. If that number equals 1, well, that means it's inconclusive. The ratio test doesn't work when you're having a limit of 1, and therefore you have to do something else to figure out what's happening. Now, the way we get to use the ratio test is we are going to take this expression here and apply it to our power series. And then we want to focus on this conclusion right here where it's less than 1. So let me write this up on the board. You guys are writing this in your notes. And then we're going to do that example. So let me write down on the board, we've got the ratio test. So the ratio test tells us to look at a limit, and that specific limit is the limit as n goes to infinity of the absolute value of a to the n plus 1 over a to the n. This is a tool that we can use to determine the convergence and divergence of a power series. If that limit is less than 1, it means our series absolutely converges. If that limit is bigger than 1, including infinity, it means that our series diverges. And if that limit equals 1, it's inconclusive. It means we need to test farther. Conclusive. We need to test another way. Alrighty. So we're going to apply this to our series example, our power series example, and see what's happening. See how this applies to our power series example. So our power series that we're testing is 3x minus 2 to the nth over n. And so our first step is to take this series right here, and we're going to look at the n plus first term and the nth term. And we're going to take a limit as n goes to infinity. So that's our first step. We want to look at the limit as n goes to infinity of the n plus first term over the nth term. And what does that look like? Well, that simply looks like taking the limit as n goes to infinity of the absolute value of 3x minus 2 to the n plus 1. So we just put n plus 1 wherever there's an n to start. Over n plus 1, all divided by 3x minus 2 to the n over n. And so some of you guys started this last week in recitation, and some of you started this Monday in recitation. And now we want to simplify this expression. So this is where we're starting. We're starting with this limit, and we want to simplify this expression. And so a key is to break up this power right here. And remember, when we have rules for exponents, if we have e, for instance, to the x plus 3, we could divide that up as e to the x times e to the 3, because if you have like bases, you add your exponents. So we're going to break up this right here and say that this is equal to the limit as n goes to infinity of 3 to the x minus 2 to the nth power times 3 to the x minus 2 to the first power over n plus 1. And not only that, but now I'm going to take this bottom fraction down here, I'm going to flip it over and multiply. So then I'm going to take that bottom, flip it over, and multiply. So I get this expression here. I want the limit as n goes to infinity of 3x minus 2 to the n times 3x minus 2 all over n plus 1 times n over 3x minus 2. Everybody okay? And what do you see? Max, what cancels in here?
3x minus 2 to the n.
Yeah, 3x minus 2 to the n is my term that is going to cancel. And so what I'm left with, and I'm going to put it down here now, that's the limit as n goes to infinity of the absolute value of 3x minus 2 to the n over n plus 1. Now, when you guys take, how many of you guys are taking Calc 3? Is anybody take? Some of you guys are taking Calc 3. So when you get to Calc 3, you're going to be talking about having multivariables in integrals, multivariables and derivatives. And so you're going to take partial derivatives and things like this. So if I want to take a limit as n goes to infinity, notice I have multiple variables here. I have an x and I have an n. But the limit is only applying to n. That means x gets treated like a constant. So 3x minus 2 is just a number in our heads. It's just a constant. It doesn't affect the limit. So we can, and this is how I like to view it, we can take that constant and just pull it right out front and not worry about it because it's not being affected by the limit part. So I can look at that and pull it right out front and just look at what's left over, which is n over n plus 1. I like to do it because it cleans it up. You don't have to do it this way, but to me it just cleans it up a little bit. It's a constant. I'm pulling it out front. That's leaving me with the limit with n over n plus 1. Now, how do I do this limit? I get infinity over infinity, right? So we could use L'Hopital's rule, take derivative on top and derivative on the bottom. Or we could just look at highest power on top, highest power on bottom, and cancel, right? There's lots of ways. No matter how you slice it, let's say we took the derivative on top and the derivative on the bottom using L'Hopital's rule. What limit do we get there? 1 over 1? 1 over 1, yep, 1 over 1, which is 1, right? And 1 times the absolute value of 3x minus 2 is just going to leave us with 3x minus 2. Okay, so we're doing a lot of work. Let's remind ourselves what we're doing. We are trying to find the interval on which this power series converges. Because it's not geometric, we're applying a ratio test. And our first step in applying the ratio test is we want to take a limit. Once we get the answer for our limit, now we can go on and look to step 2, which is what do we do with this limit? Well, now we look at the conclusion we want. We want this power series to be convergent. So that means we want to make this limit and make it less than 1, right? Do you guys see that? And so that creates for us another 3-part inequality, which we are getting really, really good at evaluating. So set yourselves up this 3-part inequality. And I get this. So it's telling me so far that my interval of convergence is going to be 1/3 to 1. But the ratio test also has this other condition down here. And that says that when this thing equals 1, I don't know what's happening. So I have to investigate farther. And so what that means to me is I have to say, what happens when 3x minus 2 equals 1? Well, that happens when 3x minus 2 is 1 or negative 1, or in other words, that happens when x is at my 2 endpoints over here on my interval. When x is 1/3, it's going to give me negative 1. When x is 1, it's going to give me positive 1. And so I have to investigate these 2 endpoints. And so what we say we do on the very last step here is we check our endpoints. And that means we take 1/3 and we go back to the very, very beginning and we look at our original series, which was 3x minus 2 to the n over n. And in place of x, we put 1/3 and we say, what's happening? And then in place of x, we put 1 and what's happening? All right, so let's go back here then and let's do this last step, which is checking our endpoints. So when we put 1/3 back into our original series, we have 3 times 1/3 minus 2 to the nth. What's that giving us? Negative 1 to the n? Is that right? Because 3 times a third is 1. 1 minus 2 is negative 1. Okay, so what does this thing do? What is it? Drew? It's conditionally convergent because it's an alternating harmonic series. Yes, this guy is conditionally convergent. So that means x equals 3 is good. This guy is good. It means my series converges here. How about at x equals 1? So let's test x equals 1. Do the same thing. Put 1 back into that original series in place of x. So we have 3 times 1 minus 2 to the nth power over n. And 3 minus 2 is just 1 to the n, which is just 1 over n. And this guy is the harmonic series that diverges. So that means he's not good. But let's summarize then in step 4. So that means our interval of convergence is step 2, 1/3 to 1, combined with step 3, which says we have to include 1/3 but disclude 1. And so we would say that our interval of convergence for this power series is 1/3 closed to 1 open. Does this make sense? When you're presented with a power series, that is a series that has x's in it, and you want to find the interval of convergence. If it's geometric, you can just find it. But if it's not geometric, you want to use the ratio test. Ratio test actually also works for geometric series. It always works. So use your ratio test. That is, take a limit of the n plus first term over the nth term, set it less than 1, and don't forget to check your endpoints. Alrighty, I want to give you 3 series to try, okay? I'm going to give you 3 series to try unless there's any questions. How are you guys, okay? So I'm going to give you 3 series to try. Sometimes some funky things happen. So did anybody do the homework yet? Did you do the homework yet? Not yet. Nope. Somebody did. So sometimes funky things happen, right, Drew? So let's take a look at some different examples and see. So for each of these power series, find the interval of convergence for each power series. So, first example, A. I want the series x minus 6 to the nth power over n factorial. The second one I want is going to be the series, n equals 1 to infinity, n equals 0 to infinity of x to the n over n plus 5 times 3 to the n. And then the third one I want to test is n equals 0 to infinity of negative 1 to the n times n factorial over x minus 5 to the n over 5 to the n. Alrighty, let's test and find the interval of convergence for each of these power series. And I'll wander, and that way you can ask me questions. Keep tripping on my feet, tripping on desks. So the first guy we got that it converged.
I can't see the last one.
Oh, the last one. Let me pull him over. Sorry about that. So the last one that we're working on is this one right here. So I'll just put the answers. So this guy converges the top one converged from negative infinity to positive infinity. That was his interval of convergence. The second one converged from negative 3 closed to 3 open. And the third one, I'll do him in pink. What does he do? This one's tricky. I'll put a big smiley face there. This one is tricky. See what's happening. And so, as long as x minus 5 is some number, so as long as it's a number not equal to 0, then this gives you infinity. And so that is always bigger than 1, and therefore the series always diverges. Except when x equals 5, that makes that second quantity 0. And 0 times infinity is an indeterminate form. So if you check when x is 5, that gives you negative 1 to the n factorial times 5 minus 5 to the nth, which is just 0. And so that actually just gives you an infinite sum of zeros, which automatically converges. And so this last one, it's tricky, but
Why are we checking x is 5?
Because here's why we're checking x is 5. Because we get infinity, right?
Yeah.
We get infinity for this limit part right here. Now, infinity times any number is infinity. So this diverges always so long as you get a number that's not 0. Infinity times 0, this is an inconclusive statement. We don't know what infinity times 0 is when you're talking about limits and things involving that. So you have to be very careful when you have 0 here. And so that's why I said, well, we have to check x equals 5 because when x is 5, it gives me a 0 there. So you want to check that place. And if you put it back into your series, you note that you actually get an infinite sum of zeros. And when you have an infinite series of zeros, or 0 plus 0 plus 0 plus 0, that always converges to 0. And so we would say that this interval of convergence is the single point. It's what we call the center point. It's the point at which the series is centered around. It's the point that would give you a 0 in here. If you put x minus that number that gives you a 0 in here is your center point for this series. So on web work, you'll have to put in curly brackets with that center point to say that's my interval of convergence. It's actually 1 point, just the number 5. How are you guys with those three? Did you? It's just the number 5. It diverges everywhere else. That one was tricky. Diverges everywhere else. So I just want to state that there is a conclusion, and I just want to kind of summarize that when you have a power series, this particular power series is said to be centered at A. Okay, this guy's said to be centered at A. And anytime you have a power series, you have 3 possible intervals of convergence. Number 1, it's when it converges only when x is A, or in other words, that's what we just did, where your interval is actually just the point. It converges for all x. And if it converges for all x, that means we're converging from negative infinity to infinity. Or there's some r so that you have an interval of convergence based on r, whatever r is. So whatever that region is, that's what we did last, where we had these intervals and we then tested endpoints. That's the last case, where you have a specific finite interval, where your endpoint may or may not be included in that interval of convergence. So it may or may not be closed, depending on what your series actually is inside. So those are your 3 places. That's kind of the last bit of the power series.